Hi, I welcome you to this lecture on Axial Flow Compressor. In the previous lecture, we discussed about the work absorbing capacity of a compressor blade. In this lecture, we will be discussing about a term called as degree of reaction, which tells us more about the enthalpy change in the rotor and as well as in the stator. Let's begin. So we will have a quick revision of the HS diagram, that is the enthalpy entropy diagram. So as we discussed in the previous session, so the process starts from state 1, goes to state 2 and then reaches state 3. So 1 to 2 is the rotor stage and 2 to 3 is the stator, right? So the air enters the rotor and leaves the rotor at point 2 and enters the stator at point 2 and leaves the stator at 3. So during the process, the kinetic energy is increased in the rotor, and then that kinetic energy is being transformed into the pressure energy in the stator. Now we will try to understand how exactly the enthalpies are changing in the rotor and as well as in the stator when compared with the whole stage, right? So the degree of reaction is defined as the distribution of pressure rise between the rotor blades and the entire stage, right? So it is actually the ratio of the change in enthalpy in the rotor to the change in enthalpy in the stage. So many of the times when recalling this equation, you might confuse the stage with the stator. So remember one thing. Whenever we supply the work to the compressor, we are actually supplying the work to the rotor blades. Only rotor blades are consuming the work and not the stator blades. Stator blades are stationary, they don't need any work input. Whereas to compress the air, it needs to be accelerated, and that part is done by the rotor blades, and to do that we need to supply the work, right? So remember this point. The degree of reaction is always the ratio of the change in pressure in the rotor to the change in overall pressure in the entire stage. Now this I can represent it in terms of enthalpy as well as the temperature change, and it tells that the enthalpy change in the rotor is represented by H2 minus H1, and the enthalpy change in the entire stage, that is H3 minus H1. So in the rotor, you please observe here, it is just H2 and this is H1. So these are all static enthalpies. And then in the entire stage, it represents H3 minus H1, that is in the denominator. Now it tells how much pressure rise happened in the rotor when compared with the total pressure rise. So it will always be in terms of percentage, right? So let's say 50% degree of reaction means the total enthalpy change is shared by rotor and stator 50%, right? So 50% of the enthalpy change happens in the rotor and 50% happens in the stator, right? Similarly, the higher degrees of reaction, let's say 60%, 70% and so on. So in those cases, the degree of reaction tells that 70% of the change in pressure or change in enthalpy is happening in the rotor stage, right? There are low degree of reaction machines as well. So we will go in depth into that in the later lectures. Also, I can represent the degree of reaction in terms of temperature. Right? So in the previous class we discussed the relationship between enthalpy and temperature. So del H is equal to Cp del T. So they are directly related. Whenever temperature increases, enthalpy rise will take place, or the vice versa. So I can replace the enthalpy with the temperature values for better understanding of degree of reaction. So let's call this as equation number 22. Now if you try to recall the concept of no inlet guide winds. So in that case, the absolute velocity at the rotor entry is equal to the absolute velocity at the stator exit, right? So C1 is equal to C3. Now for this assumption, then the static enthalpy change is same as the stagnation enthalpy change, right? So this is a very interesting concept to understand. This is the case only when the inlet guide winds are absent, because if inlet guide winds are present, C1 is not equal to C3. So please remember this. The absolute velocities are assumed to be constant only if inlet guide winds are absent. And at this point, I would like to differentiate the axial velocity and the absolute velocity. Okay, please understand. The axial velocity is CA, the absolute velocity is C1. Okay, here we are talking about the absolute velocity, right? So the assumption is the absolute velocity remains constant. That means C1 is equal to C3. So for that case, the static enthalpy rise, that is H3 minus H1, is same as H03 minus H01, right? So this rise remains same, and that I can convert it into the velocity parameters, that is uct2 minus uct1. So this is the change in the energy from inlet to exit, right? So that, let's call that as equation number 23. At this point, kindly recall the work whatever we are supplying to the compressor stage is absorbed only by the rotor blades. Stator blades doesn't need any work input, right? So this point I would like to highlight here. Now, however, if we assume the relative stagnation enthalpy, so that remains constant in the rotor. Although the stagnation enthalpy changes, but the relative stagnation enthalpy remains constant. When I say relative stagnation enthalpy, it is a relationship between the static enthalpy and the relative velocity, right? So that is why relative enthalpy. Okay, so relative enthalpy, the stagnation state is equal to the static enthalpy plus the dynamic enthalpy, that is with respect to the relative velocity. Okay, so please make sure that you're talking about W when you say that the relative enthalpy remains constant in a compressor stage. Okay, that's to be specific in the rotor. Okay, so the inlet stagnation enthalpy, that is for the rotor, is the same as the outlet stagnation enthalpy with respect to the relative velocity. Okay, please make sure of W. Okay, if we are talking about W, it is not C absolute velocity, or it is not about axial velocity. It is about relative velocity, hence the relative enthalpy. So let's call this as equation number 24. Now let's substitute the value of equation number 23 and equation number 24 in equation 22. Okay, so we'll try to understand how meaningful we can explain the degree of reaction, so that if I know certain parameters, I can calculate the degree of reaction, right? So that we will try to understand. Now let's substitute equation 23 and 24 in equation 22. So means equation 23 is for denominator, and equation 24, if I bring the exit static enthalpy to the left hand side, or you make the manipulation, so you get H2 minus H1, that is the numerator part, right? So substitute these values in the degree of reaction equation. We are going to get half W1 square minus W2 square divided by U CT2 minus CT1. Now this is also a very significant equation in terms of velocities, right? Now suppose I don't have the values of velocities, so definitely I need some other parameter to arrive at the degree of reaction value. Now let's try to convert these velocity terms into the air angles and the blade angles. Okay. So I'm just going to substitute each value from the previous expressions discussed in the previous sessions. So I'm just going to substitute the value of relative velocities and the tangential component of the absolute velocities in terms of blade angles. So I'm going to get CA square multiplied by tan square beta 1 minus tan square beta 2, and in the denominator you have 2u multiplied by CA into tan beta 1 minus tan beta 2. Now this is a very interesting mathematical expression, and I can simplify it to this below equation, that is half of CA by u multiplied by tan beta 1 plus tan beta 2. Now it's a very simple process. So numerator, it represents a square minus b square, so I can convert it as a plus b into a minus b, and a minus b and a minus b will get cancelled from numerator and denominator. So in the numerator I am left with only tan beta 1 plus tan beta 2. Now this equation is in terms of the blade angle or the relative air angle, right, beta. Now if I want to convert it into the absolute air angles, that is alpha, so you just add and subtract tan alpha 1 to the expression. So I'm going to get another expression which is 1 by 2 minus 1 by 2 into CA by u multiplied by tan alpha 1 minus tan beta 2. Right. So let's call this as equation number 25. Now the difference between this equation and equation 25 is equation 25 includes the absolute air angle as well, that is at the inlet, right, that is alpha 1. Now this is important in terms of the practicality of the problem. So in the next session, when we solve problem, you will understand why it is important to represent the degree of reaction in terms of air angles and blade angles. Yes, of course, if on the right hand side, if velocities are present, still I can calculate the degree of reaction if and only if I know the values of the velocities, right? If velocity values are not known, then the only parameter that are available for the designers are the air angles and the blade angles, right? So we utilize air angle and blade angle and derive the degree of reaction, right? So this is very important from the design point of view. So these are the observations. One is that this form, that is equation number 25, is the useful form of degree of reaction, right? So there is another form as well, right? So this is another form in terms of velocities, and again we have another form in terms of enthalpy, and there is third form in terms of temperature as well, right? So there are 4 forms for degree of reaction depending on the available values, right? So as a design engineer, I am more inclined towards the geometric parameters that are air angles and blade angles, right, rather than the physical parameters like velocities, right? So at this point, kindly note these very important observations. So degree of reactions can be expressed in terms of temperature, enthalpy, velocity parameters, and air angles and blade angles that are geometric parameters, right? So we will end this session now. In the next session, we will discuss about a few numericals where you will have a clear understanding of the theory you learned about the axial flow compressor, right? Thank you.